Swayam Prabha. Digital India. Educated India.
Okay, we'll begin again after this break of a week. So, let us see what we have done so far. We decided that instead of looking at the eigenvalue problem, we would be better off looking at the receptivity problem. The distinction being that in a receptivity problem, you prescribe some kind of a definitive boundary conditions, right. So, for the flow past a flat plate, what we decided to do is still look at the linearized Navier-Stokes equation, because we are looking at small disturbances imposed. And if we look at that linearized Navier-Stokes equation in the alpha omega plane, that is the spectral plane, then we end up getting the Orr-Sommerfeld equation. That is what we have written here. So, Orr-Sommerfeld equation is basically the unit around which all this discussions that follows will revolve around. So, what we had done in eigenvalue analysis, we given all kinds of homogeneous boundary condition. For example, this is quite a favorite condition to invoke, that if we are talking about disturbances which remain embedded inside the shear layer, then if you go outside the shear layer, those disturbances are not there. And that is the statement of equation 58, which says that if you go far away from the wall, your velocity components have to be equal to 0. Now, what we are talking about in this particular lecture and a couple of lectures to follow is we are going to study what is called as receptivity to wall excitation. So, we want to find out how your shear layer is receptive to disturbances, and what kind of disturbances? These are imposed wall excitation. Kind of excitation that we want to discuss, we talked about it, that it is going to be the nothing but your those impulse response that we talk about. Impulse response means we are going to excite the boundary layer at a fixed location. Okay. So, if we look at the schematic a bit, this is how it should look like, that we have a flat plate here, okay, and over which a boundary layer develops. Since the flat plate has a very sharp leading edge, so we will have a boundary layer originating from there. And now, what we want to do is we want to make use of this Orr-Sommerfeld equation, and I would try to tell you what we how we got this. We got this because we made some vital assumptions. What was the prime assumption? That the flow is parallel. That means, we are going to talk about that part of the flow where the boundary layer does not grow anymore. So, maybe I mean, we would exclude this part of the flow where you can see a significant growth of the boundary layer. That part is not considered, but in this part this works. So, if I want to study the property of the shear layer to wall excitation under the Orr-Sommerfeld umbrella, then I would provide a localized disturbance like the one that we noted was performed by Schubauer and Skramstad. Now, this is a delta function. So, what I could do is I could actually fix a coordinate system like this. My x will start from here, y will go from there. See, as far as the parallel flow is concerned, there is no origin. It is supposed to be coming from minus infinity going to plus infinity, but it is the location of the exciter that imposes a coordinate system. So, we decide to have the origin there. Okay. So, basically then what we are going to do is create a kind of a mass source which is given by a delta function. Okay. And then this mass source is going to eject mass and suck mass half the cycle each. So, we are basically going to give some kind of a time variation like this. And where is this omega naught here? This is here. See, here is omega naught by alpha. Right. Then what happens? Delta function's Fourier transform, Fourier Laplace transform is 1. So, that is what happens, that this has a Fourier Laplace transform which will be given by some 2 pi due to this part. This 2 pi is the normalization coefficient. So, it is the relationship between direct and inverse transform. What about this one? This one we are assuming that signal problem, that excitation is at omega naught only. Okay. So, that is what it is. Then what happens is, talk about phi. What was phi? Phi was the amplitude of the v velocity. So, this kind of a source here is equivalent to creating a one normal velocity, right. Half the cycle it is plus, half the cycle it is minus. And then if I have v of x y equal to 0 and t is given by delta x e to the power minus I omega naught t. Okay. And what was this defined as? If you recall, your definition of big was like this. This was our definition, right, and we had kind of 1 over 4 pi square, and this was the expression that we had. So, now if I club these two together, what will it give? It will give me phi at y, right, equal to 0, because we are applying it at the wall. Okay. And it will be also a function of alpha, and because of the signal assumption. So, this will be nothing but simply equal to 2 pi, right. It will be just simply equal to 2 pi. Now, what have we had so far? We had phi given as a1 phi 1 plus a2 phi 2 plus a3 phi 3 plus a4 phi 4, and what we found that phi 1 goes as e to the power minus alpha y, phi 2 goes as e to the power plus alpha y, phi 3 goes as e to the power minus q y, and phi 4 goes as e to the power plus q y. This is what we get as we go out of the shear layer, and you recall that q square was alpha square plus I r e u minus c. Okay. Then those two conditions given by 5.8 equation 5.8 here would imply that if alpha, the real part of alpha and real part of q are positive, then this must be equal to 0. Please do understand, we are not saying phi 2 or phi 4 equal to 0, we are saying that constant has to be equal to 0, right, to satisfy those two conditions, vanishing conditions. So, this then would give you what? this would give you A1 510, okay, plus A3 530 should be equal to 2 pi. That is what we have written here, this equation. The last equation is that. Okay. And what about the other condition? Other condition is u equal to 0. What is u? If you recall, the mass conservation equation gives us what? Mass conservation equation, we did get that I alpha f is equal to phi prime, right. So, if f is equal to 0, then phi prime has to be equal to 0, right. So, that you have done. So, basically we need to also have phi prime at y equal to 0 for all alpha must be identically equal to 0, and this gives you this. So, that completes your description of receptivity, right. So, this is your definitive excitation provided at the wall, which is of this kind. That translates to this two boundary conditions. So, now it's more definitive in the sense we can now fix the value of A1 and A3 by solving this equation. This was not there in the case of eigenvalue problem. We had no idea of what A1 and A3 was. We expected that somehow A1 and A3 will materialize. Now, if we do this as we continue solving these two equations, we get the value of A1 and A3. That is very easy. You do that and plug it back to your equation. Now, what have we done here? Instead of writing v, I have written in terms of psi. It is the same thing. You can see the one-to-one correspondence between v velocity and psi component, because if I take psi like this, v will be what? D psi dx. So, that will be simply nothing but I alpha multiplying this phi. So, that is why I am saying that wall normal component of velocity and the stream function has the same structure, and since we are putting in some kind of a mass source, so it is better that we work on psi, and that is what we have done, and solve for A1 and A3 and plug back the whole thing, and this is what you get. What is A1? A1 is phi 3 prime 0 divided by this quantity, and what is your A3? A3 is minus phi 1 prime 0 divided by this quantity. And what is this quantity? It is very familiar to us. This is nothing but your characteristic determinant. This is how we defined as the dispersion relation. This is how we defined as the eigenvalue relation, right. So, that is how it appears. Now, you can very clearly see the role of dispersion relation. Dispersion relation works like an amplifier, because it is in the denominator. So, in the neighborhood of the eigenvalue, what it does? This quantity approaches 0. So, whatever the excitation field is, that gets multiplied by a very large quantity, and so that is how you should really interpret eigenvalues. Eigenvalues are nothing but it is not black magic, it is very definitive. That is why you see the connection, that when you pose it as an impulse response, the characteristic determinant or dispersion relation appears as the denominator in this form, that it appears in numerator by denominator. Then what happens? Now, you see that is where your mathematics comes in, that if your denominator is 0, even if the numerator is 0, there is always the possibility that you will have a finite excitation. This is what actually drives stability analysis on, saying that even in the absence of disturbance, I will have a 0 by 0 form, and that may relate to some finite. However, from a physical point of view, as practicing engineer and scientist would like to interpret it, that you probably would not have the numerator virtually equal to 0. There would be always some disturbances in the background. And if those disturbances also inhabit near the dispersion relation, then of course, you will get an amplification. There is though a case by which you could switch off this quantity. Suppose I can reduce the magnitude of this quantity phi 1 prime 0 and phi 3 prime 0. Then what will happen? If I keep on selectively removing them, I will not see that in the response. Remember the experiment of Reynolds? Remember the experiment that I showed you, that flow past a cylinder for Reynolds number 53 case? For different speed, I have different background disturbance. And that was your question in the mid-sem. Reynolds experiment relates to, is it a question of nonlinearity or it is a question of receptivity? To me, it appears it is a question of receptivity. If I can stop the background of that particular class of disturbance where the dispersion relation resides, I will not have that response. And that is why people have gone ahead and obtained Re critical for flow past a cylinder to a very, very large value. That has gone as close to as 100,000, while Reynolds obtained it around 12,830. What it essentially tells that as an engineer, if you had to design something, you can always design a device where you could subdue this disturbance at that critical points, at the dispersion relation point, at the eigenvalue relation point, and you can do that. And this is what you see in most of these aircrafts which uses so called natural laminar flow airfoils. There the contouring of the airfoil is done in such a manner, it is a passive device, you are not exciting a ribbon or something or anything of that kind, but you contour the profile in such a way that your pressure gradient is such, the curvature is such that your background disturbances which are there, they do get less receptive. Because what happens? By changing the pressure gradient, what am I doing? I am changing u, I am changing u double prime. So, you can see the transfer function of the system can change. So, now you see the another aspect of the designer activity that can relate to what we are discussing. There are two aspects. If I want to do something, if I decide to control some observable phenomena, then there are two ways of doing it. Number one, stop the input. Number two, change the transfer function. So, what you see in all Boeing 757 onwards, or what you see in Airbus 340, it is basically a desire to change the transfer function, because it hardly ever happens that you can change the input in a real life. Of course, you can select your cruising altitude, etc., etc. But if you are an airline operator, you will have to be flying at considering other considerations. For example, you would be looking for fuel economy that will decide upon your altitude, flying altitude. So, these are some of the issues that are very, very relevant, still not completely digested. We do not have given out all the proper way of how to handle these issues. For example, talk about this clear air turbulence. There is a case by which we have figured out that if you have a vortex, atmospheric convected vortex is approaching the aircraft wing, then a pilot can decide whether to go over it or below it, provided he knows the sign of the vortex. If you are talking about a vortex which is counterclockwise rotating, it would be very, very advisable for the pilot to duck under it, and then instead of destabilizing the flow, it will stabilize the flow. We will come to that discussion in the next topic. But what I am saying is now, let us not jump the gun. We have two quantities at our disposal. One is controlling the input, the other is controlling the transfer function. If you are a designer in the shop floor, you would rather change the transfer function, you do not get to change the inputs. Whereas, if you are an experimentalist, you are interested in understanding the flow physics, then you do play around with the input itself. So, these are two different complementary activities, right. So, now what we are going to show you is a very, very clear cut case. We take a Blasius boundary layer and we take a Reynolds number of 1000, that would perhaps contribute to somewhere here. So, where we have some kind of a parallel boundary layer, this delta star relates to the displacement thickness, okay. And we have already seen that Reynolds number of 520 is about the point where flow becomes first critical. So, 1000 is far into the supercritical range, and we are talking about omega naught equal to 0.1, that would sit somewhere in the middle of this neutral curve. So, it will be quite perceptible disturbances that you are going to see. Now, let us move ahead and see what it looks like. It looks like what we also get a qualitative picture from stability theory, that we see the disturbances plotted at two heights. The one, the solid line, it is the outer part of the shear layer, and the larger amplitude is the one that is closer to the wall. So, that is called the inner maximum. Okay. So, you will see that if I plot the disturbance velocity versus y, the disturbance velocity looks like this. Okay. And this is what is called as the inner maximum. And this part is called the outer maximum. So, basically talking about the magnitude, the disturbance quantities have two maxima, one here, one there. If I were to ask you which one would you prefer, of course, you would point out this one, because it is a larger signal that you would get. This magnitude is much larger compared to this, and that is what you are seeing here. The inner maximum has a larger amplitude compared to the outer maximum. But what happens is, this is very narrow, and if you are trying to do a measurement, if you are an experimentalist, it is rather difficult. If you miss it, if you are not there, if you are slightly, the signal will be there, right. So, tracking the inner maxima exactly is not a very straightforward issue. So, experimentalists like to focus on the outer maximum. So, that was one of the reasons that we plotted this, and you can see what the linear theory did talk about. The amplitude decays exponentially, like what we wrote here, right, e to the power I alpha x minus omega naught t. So, with x, the amplitude is growing exponentially. However, of course, your stability theory would not be able to tell you this part of the solution. This is what we call as the near field of the solution, because where is your exciter? Exciter is at the origin. Exciter is the origin. So, the receptivity theory actually tells you that what happens in its immediate neighborhood and what happens asymptotically far down. So, stability theory basically tells us what happens far away from the exciter. So, this is something we need to understand. I will talk about a couple of theorems attributed to Abel and Tauber shortly, and then you will see that this is what we would expect, because we have talked about the complementarity property of Fourier transform and the direct inverse, and the inverse transform and the direct transform. What did we see? That if a quantity is localized in space, then in the k space it is sort of all pervading and vice versa. Now, if I want to see something which is far away from the source of excitation, then what should I have? That point would be where? That should be in the unstable part, and for x positive what should be the nature of alpha? Alpha I should be negative. So, what happens is alpha I negative values, if they are there, then you are going to see it everywhere, all x. But what happens in a realistic flow like what we are studying here, even a gaseous boundary layer, these points are very close to the origin. So, what happens that you are going to see a kind of a moderate growth. Okay. So, we will again come back and talk about that couple of theorems, and we will find out what happens is that if we try to talk about this in the neighborhood of the exciter, where should we look at in the alpha plane? This we should look at far away from the origin, because it is the complementarity problem. If I want to see at x equal to 0, I should look at alpha equal to infinity, and if I want to look at x equal to infinity, I should do it very cleanly near the origin. This is the complementary property that we talked about. So, this is one of the finest achievement of the receptivity theory, that we get a composite picture. In fact, not many people before 80s had good appreciation of this thing, what we just now saw. The disturbances do not appear in a discontinuous manner. If I were to switch back to the previous one, we can see that despite the fact that the exciter is placed here, disturbance does penetrate little bit upstream. How far this is? This is not very much. This is about 30 to 50 delta star. Okay? And the penetration is restricted, but it is still in a continuous manner. If you look at any book except this one that we are following here, you will find that they just simply do not dare say what is here. They will just simply say something happens here and then we get this. But I must also tell you that if you look at even in the positive x side, immediately on this side of the exciter, the properties do not correspond to what you see in there. Why? Because that is what I told you. In the neighborhood of x equal to 0, the contribution does not only come from the eigenvalues, it does come from alpha going to infinity also. That is what we would expect. So, do understand that the near field has this particular feature which do not reflect what your eigenvalue analysis tells you, and stability theory would never tell you that part. Okay. Now, I already said it, that the near field response that we see is due to alpha going to infinity point, and what that is called? That is called the essential singularity, that you have done in your complex analysis course, right. Like if I talk about e to the power z or sin z or cos z, they are not defined. When z goes to infinity, those points are called the essential singularity. So, here also in the alpha plane, alpha going to infinity would be the essential singularity, and I explained to you why it should be so. Because they will contribute significantly to your near field response. So, there is a case for obtaining the contribution from the essential singularity alpha equal to infinity. that we should try to plug it in this kind of a relation. This is your physical variable and this is its transform. So, that is what we say, the original image pair we should know. Now, if you recall, when we were discussing about the Cauchy integral and the properties of the eigenvalues, what did we see? We used that Cauchy's integral formula and we indented the contour around those eigenvalues and closed it. However, what you also did, suppose I have an eigenvalue here, then what I said, that I will go along the Bromwich contour, and let us say the Bromwich contour is along this axis. Okay. And then I decide to close it from this side, and then what I said, I must bypass and close the contour like this. Remember, this is what we had done. So, we are showing the connection between receptivity theory and instability theory time and again, and this is the way we go about doing it. We exclude the singularities, so that the function is analytic everywhere, and then we say by Cauchy's integral formula it should be equal to 0. It should be equal to 0, it is fine, but then it has a couple of contributions. One comes from the Bromwich contour, other comes from the contour which is in the upper half plane. Now, when we say that the contribution coming from Bromwich contour is equal to sum of the contributions coming from the residue at the poles, that is where we assume that the contribution along the semicircular arc is 0. And when we do that, that is what we call as the Jordan's lemma. Well, I jokingly actually call it Jordan's dilemma, because it so happens that in this particular case, you will see that it is not always given that this quantity will be equal to 0. Unfortunately, in your probably a maths course, you have handled very nice, well behaved functions which satisfy Jordan's lemma. Nobody has shown it so far that Jordan's lemma holds even for this Orson field equation, and we did try doing that. But what Jordan's lemma stems from is this observation that if I am performing a contour integral of this kind, then this phi of alpha should have this kind of a structure. It should have again a numerator by denominator, like what we saw in the morning today itself. However, it should not be only be in a rational fraction kind of a thing, but the order of the denominator must be at least 2 degrees higher than the order of the numerator. If it is not, then you cannot show that Jordan's lemma is valid. So, the task is very simple. Task is very simple for us to investigate. We need to figure out for our case the solution of Orson field equation phi of alpha as alpha goes to infinity. What is the order of the numerator or denominator? It is very, very interesting that about more than 20 years ago, I did sit down and work it out. There is another philosophical issue that often remains unsaid in most of the stability approach, is that if I were to be only depending upon the eigenvalues, then when and how I can express the disturbance field in terms of these eigenvalues. If they are finite in number, it is virtually impossible to describe any arbitrary function, right. My disturbance environment could be anything arbitrary, and if I have only a finite number of eigenvalues, then I have a problem. So, people have tried to address this issue. They tried to say, oh, something somewhere must give rise to a helping hand, so that even with a finite number of eigenvalues, we can describe any arbitrary disturbances. Now, you look at this simple case what we were looking at? We were looking at the receptivity of the Blasius boundary layer for Reynolds number of 1000 and omega naught equal to 0.1. And we now know how to find out all the eigenvalues in a finite part of the domain by that grid search method we have studied. So, if I do the grid search method for this parameter combination, lo and behold, you only have 3 modes, and those 3 modes are of course ordered in this particular manner in the way the magnitude of alpha I increases. What is the first one? First one is unstable, right, with a minus sign. This is what is called as the Tolman-Schlichting mode or Tolman-Schlichting waves, right. This is what Tolman and Schlichting first found out, and your eigenvalue analysis tries to obtain this. Eigenvalue analysis can also hope to find others, but to my utter amazement, about more than 2 decades ago, I found these are not very well done, and we developed the compound matrix method, and we used the grid search method, and we figured out in a box in a alpha plane, say of size 2 by 2 on all sides, and we only figured these 3 eigenvalues. These eigenvalues, this last 2, as you can see, comes with a plus sign. So, if they were to be going downstream, they are stable modes. How do you find out which way they are going? Calculate the group velocity, and we calculate the group velocities. All of them are positive. So, they are all downstream propagating waves, and then this is an unstable wave, and these 2 are stable waves. Now, my question that I asked you about that with only 3 eigenvalues, can I hope to represent any arbitrary case? You have already seen, with the help of Fourier series and Fourier transform, we try to express any arbitrary function in terms of infinite number of terms, right. A finite number of terms will not allow us. There are lots of activities at the fluid mechanics and physics community in trying to say what it is. Now, you see what it is. People of course barked upon the wrong tree. They did not look at the Jordan's lemma path. Instead, they said somewhere from somewhere else something is coming, and this somewhere or something they attributed to as the a continuous spectrum. Where would this continuous spectrum be? Well, for example, if I am plotting in alpha r, alpha I plane, you see all these concepts holds good if we are not along the imaginary axis. If we are along the imaginary axis, then can we say A 2 and A 4 going to 0? We cannot say that. So, one group of people did say, look, maybe along this axis we have a contribution coming from all the points, and this is what they called as the continuous spectrum. Now, that is about A1, A2 contribution. What about A3, A4 contribution? That depends on Q. Q also can be purely imaginary. Expression is given, you can work it out. I will give it to you as an assignment, work it out and find out the curve or curves along which Q is purely imaginary. And if you have such a curve which you would be able to see, there would be 2 such curves along which Q is imaginary. One such line will be there, well, originating from some point where Q will be exactly equal to 0, and then you will see it will go along this, and then you will have here. Similarly, another point would be somewhere here, and then that would go like this. So, you can work out, as I told you, that this might be one such special line, and there could be this couple of more lines on there, along which some of these fundamental modes could be purely imaginary, and then we can see. But then are the singularities, this alpha I axis or this two lines that I drew. So, I mean there is no reason why it should be, and we have already talked about while deriving the initial conditions for solving the compound matrix method, how to handle this particular transition from this side to that side. We just simply switch off this. So, is that equivalent to basically going along this and coming back and doing this? Is that what it is? That if I go all the way up to close to the origin, exclude the origin, and then come back to the other branch. So, is that equivalent to doing this? If that is so, then we cannot even have a closed contour, right? Because this alpha I axis and the semicircular arc will cross each other. I mean, it's a tough mathematical conundrum, because we are talking about point at infinity going along this line or going along by changing the radius. So, it's quite unlikely that that should come out. I would advise you to think, analyze yourself and see if a contribution from here is going to be generic for any arbitrary type of disturbances. If you have, let us say, purely imaginary exponent in phi 1 and phi 3, what kind of disturbance structure we are talking about with y? A never dying disturbances all the way up to infinity. Where do you get such disturbances? I mean, think of it. Such a disturbance will have infinite energy. It is quite impractical, but still some physicists, some mathematicians have spent some time, and there are the camp followers, which I do not subscribe to. For me, it appears that is a very pedagogic exercise, does not hold water from practical aspect, because we cannot have, see here I shown you phi structure is like this. It remains very much buried inside the shear layer. As you go out, it decays. But along the imaginary axis, I would have I want to plot phi versus y. It will basically, we are talking about some disturbances which will go like this forever. It's quite unthinkable until unless A1 and A3 or A1, A2 are also function of y. But that's not a very good thing to assume a priori, right? Because that A1 and A3 can become function of y for some other reason, not for linearized Navier-Stokes equation with parallel flow approximation. We will see that later, that when we do non-parallel theory by solving Navier-Stokes equation, we would see that there is a additional dependence with y, but that is not apparent directly from Orson-Field equation. This I know these are not so easy concept, but we need to get used to the idea of analyzing and saying what is feasible and what is not. To my mind, it appears that continuous spectrum at along the imaginary axis or along QR equal to 0 line, that is how we are going to generate, right? Along this true line, QR will be equal to 0. So, you can work out the value of QR and you can come out and tell me what this is, right? Maybe you should give it as a submission and tell me what are these two lines. Now, continuous spectrum may not do the trick, but we have already seen that there is a possibility that Jordan's lemma can be violated for Orson field equation, and that might contribute something. And this is something we did, and let me show you what we did. This is quite simple, but it was not done before. So let me explain to you how we go about doing it. What you do is basically you are trying to figure out what is the contribution coming from that semicircular arc. If I then write alpha is equal to some in a polar representation, the radial vector rho times e to the power I theta. So for simplicity, I just simply write e to the power I theta as some beta. So rho is a real quantity, beta is a complex quantity, tells you about the phase, right, cos theta plus I sin theta. You also realize very clearly that this semicircular arc is what? This is alpha equal to infinity when rho goes to infinity, right? So it's interesting that in a polar representation, the point at infinity is the whole circle when the radius goes to infinity. So you got to remember that's what we are doing. When we close the contour on the upper part, we are looking at half the contribution coming from infinity, and other half would come from the bottom. So we are looking at it that way. So let's see what happens. We are now trying to figure out what this phi is going to be for alpha going to infinity. So that means rho should go to infinity. So what happens? I can define a small parameter, call it epsilon 1, which is 1 over rho. As rho goes to infinity, epsilon 1 goes to 0. And then I have the Orson field equation. Okay. And then what I would do is wherever alpha appears, I will write it in terms of what? Beta by epsilon 1, isn't it? Beta by epsilon 1, and I plug it in and expand it. This is what I get. Okay. So basically, we are writing the Orson field equation for the limit alpha going to infinity in terms of a small parameter epsilon 1. Very simply done, right? There is no trick involved here, just to see that. However, when we write this equation down, this equation 65, we are troubled by one aspect, that here the highest derivative term is phi 4, and this is multiplied by the small parameter. So what do we get? We get a singular perturbation problem. You see, perturbation theory, as the subject was developed following Prandtl's work on boundary layer theory, has two branches. One is called the regular perturbation theory, another is called the singular perturbation theory. Regular perturbation theory behaves regularly. So where there are no issues, you can expand the problem in terms of a small parameter, and you can slowly obtain those one term after the other in the perturbation series. That's your regular perturbation theory. In a singular perturbation theory, like the boundary layer theory itself is, the highest derivative term is multiplied by the small parameter. And if we try to go through the regular perturbation theory analysis, then we see that we are not able to satisfy all the necessary boundary conditions. That is one of the problem with singular perturbation theory problem, because you cannot just simply go to the limit epsilon 1 going to 0. If you do, then immediately the highest derivative term disappears, and then you will not be able to satisfy all those 4 boundary conditions that we have been solving so far. Right? So what happens is singular perturbation theory has to be dealt with in a somewhat different manner. I would not go into the mathematics of it. It's pretty straightforward. You can look at the book by Bender and Orszag. There would be a very decent discussion. But let's see how we can go ahead and do this. So if we are now trying to do this. We are trying to find out the contribution coming for the disturbance field from phi when alpha goes to infinity. That would give me the near field response. So, there is the reason that we are calling this contribution as near field response, because we are trying to compute what is the contribution coming from alpha going to infinity, right. Well, our original problem remains as it is, right. So, we have at the wall u equal to 0 and psi equal to this, and of course, far from the wall, if we go outside the shear layer, u and v goes to 0. Well, these are the physical plane description. The corresponding spectral plane description is this, right. We have seen that this comes out like this. So, I just simply I have been sloppy. Somewhere I have left 2 pi, here I have kept 2 pi 1. It does not matter, you can scale it out. So, this comes from this condition. From this condition we get this, and these two conditions are written like this. And let us now try to solve that singular perturbation problem with these 4 boundary conditions without giving up any one of them. Now, when you look at the singular perturbation solution of an equation like what we have written, you get 2 parts of the solution, like what you have seen in the boundary layer. Boundary layer flow is what? You have a 2 deck structure. One is the inner deck, which is the boundary layer, and there is the outer deck, or which is the potential flow, right. So, in the potential flow, what you do? You allow RE to go to 0. That is what Euler did. That is what Laplace did, right. Then what do you get? You get either the Euler equation or you get the Laplace's equation. That solution is independent of RE, right. So, same thing we should do here. We will talk about outer region. So, it is very interesting. Now, sum it up for me. What we are looking at? We have a real flow which has a singular structure in terms of a boundary layer and a potential flow. Then within this boundary layer, what have we done? We have created some disturbance, and within this boundary layer, now we are talking about another singular perturbation problem. Okay? So, within the shear layer, I have a inner layer, I have a outer layer. Okay? So, this outer layer within the boundary layer should have the property you allow epsilon 1 go to 0. And if you do that in that equation that we have seen just now, I will make these transparencies available to you. So, you can take a look. The only solution that survives is phi naught equal to 0. So, it is a very clear cut thing that if you are looking at the boundary layer of the orthogonal field equation, please do understand this boundary layer is within the quotes. This is not the physical boundary layer that we have investigated so far. So, this is a boundary layer of the orthogonal field equation, and outside that boundary layer the only solution that is feasible is phi naught equal to 0. There is no problem with that. We can always have a case where in the outer part we would not have any contribution, and this is interesting. This is true for any order of epsilon 1, right. So, and what happens? This satisfies this far field condition. Why going to infinity? There is absolutely no problem. To any order you can satisfy that. What do you do when you try to obtain the boundary layer of the orthogonal field equation, or the inner solution of the orthogonal field equation in the limit alpha going to infinity? What did we do with boundary layer itself? We actually stretched the wall normal coordinate. That is why we got those similarity coordinates. If you recall from your first fluid mechanics course, when we were told about boundary layer, how do you get the boundary layer? You stretch the wall normal coordinate. So, same thing we need to do. So, we need to define a new independent variable, which we will call it as capital Y. Capital Y will be divided by the boundary layer thickness of the orthogonal field equation. So, this delta has got nothing to do with the delta of the boundary layer, physical boundary layer. This is a mathematical boundary layer of Orson field equation. So, we introduce this. Then you know all those terms that we have here, let us say for example, when I write phi prime, what I mean? I mean this d phi dy, the physical variable. Now, what I want to do is I want to introduce a new independent variable, this is y over delta. So, what I could do is basically I could write d dy should be equal to dd of capital Y times this, very easy. And what is this? Right? So, you can carry on the story further. You can obtain the second derivative. What will that be? 1 over delta square so on and so forth, and you do that. Then you see what happened. Earlier we had a term epsilon 1 raised to the power 4 and the fourth derivative of phi. Now we are writing the same thing, but now this primes refer derivative with respect to capital Y. Okay? So, we get this equation. Now, you see that was the way we handled the physical boundary layer. We are coming around the same route. So, what we are seeing here is this equation. We will start from here in the next class.